Good.
Okay. All right. Sorry for the slight delay. It's an absolute pleasure to introduce John Lee. He's a chaired professor at University of Michigan. I don't remember the names associated with the chairs.
I have a card that says.
He's an authority in combinatorics and discrete optimization and optimization in general. He's a fellow of the Informs. He's on the editorial boards of many of our top journals, particular Math Programming A. He's now the editor-in-chief of that. Are you the founding editor of Discrete Optimization?
I was the founding managing editor,
okay.
So I did all the work, but I wasn't the editor-in-chief.
Okay. So anyhow, I mean, if you guys want to chat with him, he's around until 5 o'clock or so today. He's going to talk to us about some new work he's doing on nonconvex mixed integer optimization. So without further ado, John.
Thank you, Amitabh. So it's a pleasure to be back here. So I was here 25 years ago. I think the department was named a little bit differently. Really 25 years ago this month. And I talked about a similar, at least this guy talked about a similar topic to what I'm going to be talking about today. I'm actually going to retrace through some of that. I don't think too many of you were here for that talk. Who are you? Who are you? You look familiar.
Am I?
Yeah.
He wasn't here 25 years ago.
Yeah, I wasn't
No?
here.
What about, were you
I'm
here?
the I got here in fall of '94, and I'm here
Oh,
this
wow.
1 year, so
Yeah,
nobody
I
in
arrived
here.
10 years later, but everybody was already talking about me before that.
So I mean, this is interesting. Usually it takes about 25 years for me to get invited back, and the condition seems to be that everybody has left or died.
Right.
And then the few that are still around, so John Weirman was here, James Phil was, no, none of these people are here, so they remember.
Right.
Oh,
And
maybe
that's
that's
why they're
why-
not here.
In fact, everybody who was here in March of '93 got busy today.
It's quite interesting. But things happen like that. Anyway, I'm here again. I'm back.
Welcome back.
Thank you. What I'm going to talk about is about volumes of polytopes that come up or are relevant to optimization algorithms. And some of this I talked about, as I said, 25 years ago here. And it's not that I've just been working on this for the last 25 years, but I've kind of somehow drifted back to this. And so I think it's actually kind of a cool thing that I can link this up with things that I did talk about, probably not in this room, but very nearby here 25 years ago. So the basic context that I'm thinking about, this is sort of the background context, is I'm thinking about software that actually gets applied to solve mixed integer nonlinear optimization problems. So what does this mean, mixed integer nonlinear optimization? Mixed integer means some of the variables are continuous, some are integer. Nonlinear, you all know what that means, optimization. So mixed integer nonlinear just kind of means optimization, really. So it's a way to market working in general purpose optimization. That's really what it is. So mostly what people do if they want to, sort of pedestrians who want to solve a optimization problem, is they use some modeling language like AMPL or GAMS. And this allows them to model their problem and then pass it along to the solver. And these languages basically assume that the model is what's called factorable. So what that means is there's a small library of low-dimensional functions, like things like this, functions of 1, 2, maybe even 3 variables. And every function is built up from these basic functions, these kind of dictionary functions, and also affine functions of an arbitrary number of variables. So you can think about a lot of the functions that you think about modeling with, and they have that property, that you can unravel them as simple functions of 1 or 2 variables plus affine functions. There are functions that aren't like that at all, like determinant of a matrix, things like that, which you could view that way, but it's not a profitable thing to view them that way. They're really sort of complicated functions that you can't think of this way.
Composition of these functions?
Yeah, by composing these functions. So I'll come back to some. I'll clarify that a little bit more later. But so one thing I'm thinking about in the background of all this is that there's software that takes problems like this and passes them on to solvers. And in this context of mixed integer nonlinear optimization, there's 2 basic frameworks. One is that you formulate things so that if you relax the integrality restrictions, the the feasible region becomes a convex set. And so those are kind of well-behaved instances, and there is clear algorithms, generalizing branch and bound in the linear case, and outer approximation methods for problems that look like that. But the other kind of method, when you relax the integral, you don't have convex functions at all. Often these come from engineering applications. And so you've got to do something else, which is usually called spatial branch and bound, to subdivide the domains of these low-dimensional functions, and then convexify in some way, and try to refine the convexifications, improve the convexifications as you subdivide the domains. And that's roughly what spatial branch and bound is, and there's software that does that. So anyway, I don't really mean to get into all the details of this, but that's what you should have in your mind about what I'm thinking about when I talk about the mathematical results in the rest of the talk. So, useful example, I talked about this 25 years ago here, is what's called incapacitated facility location. Let me explain what these variables mean, and then I'll describe the problem in that context. There are facilities, n of them, and there are indicator variables, yi, which tell you whether you're operating a facility or not. And then you pay a fixed cost, fi, to operate that facility. The xij variables are variables that tell you xij is the proportion of customer j demand, there's n customers, and xij is the proportion of customer j demand satisfied by facility I. So these constraints here just dictate that each customer should have their demand fully satisfied. And what you want is to make sure that if you're using any supply from facility I, that you pay for that in the fixed cost. So there's these variable costs, these transportation costs, but there's also these fixed costs. And I want to make sure I pay these. Otherwise, without these constraints here, I would just set all the yi's to 0. There'd be nothing linking the y's and the x's. So you need to link them together, and there's two well-known ways to do that, the so-called strong way and the weak way. The strong way just says, well, if this variable is equal to 0, then it shuts down all of these xij's, and you can't ship out of a facility that's closed. And if it's equal to 1, then you can set these any way you like. And this does the same thing in what seems like a more parsimonious way. It's really just the sum of these summing over j. But if you think about this, if I have this facility not operating and that's equal to 0, that shuts down all of these xij's, which are non-negative, simultaneously for that I. And if yi is equal to 1, I'm allowed to use the facility. This number here, which in optimization is sometimes called a big M, but it's a little n here, this number here is big enough so that all these variables could be equal to 1. There's n of them, and so this constraint would be trivially satisfied. So you can do it either way, and it's a well-known thing in integer linear programming that you should do the strong way, because if you relax the integrality on the y variables, the feasible region is much smaller, and when you think about the algorithms that partition space, they'll converge faster if the feasible region of the relaxation is smaller. And you can see this quite clearly experimentally. If you fix the number of facilities, just the number of them, not which ones are on, and solve this problem, what you see is that if you look at the weak and the strong formulations, you get these different objective values for different numbers of facilities. So this is the strong formulation we're minimizing, and this is the weak one. The actual integer linear programming solution with the y variables constrained to be integer are these yellow points, and they almost exactly match the strong formulation. So that's a great model of the strong formulation, and the weak one is terrible, especially for small numbers of facilities. So that's the world of integer linear programming with a linear objective function, just like I had in the formulation there, with linear objective. But the world is quite different in the nonlinear case. Let me just skip ahead. No, yeah, there. So here I change the objective function, and what I have is a separable quadratic function on the xij variables. So I have some constants times the xij squared. And you see a completely different behavior, that the weak and the strong are almost the same, and the integer solution is way up here. So we had this great formulation, the strong one, and a bad one. Now they're both kind of bad. And the question is not really why so much, what can we, it's partially why and what can we do about it. So the why has to do with what's going on with these inequalities. So as I said, the weak inequalities are just sums of the strong inequalities. So that means that the strong formulation, when I relax the y variables to be continuous, sits inside the weak formulation. But the question is, well, how much space is there between them? And there's, you can actually see this example, just trust me because I have 52 slides to go. So just trust me here that there really are points that have the y's fractional that satisfy the weak but not the strong. And the question is really what's going on with these two sets. So actually, even though the weak is weaker than the strong, it's not so much weaker at the boundary. And so you can make a simple observation that if the y's are fixed, so I tell you which facilities are open, then every customer is going to take all their demand from the closest facility, where I think of closeness as these as distances now. And so if the y variables are integer, I can, if I like, constrain the x variables to be integer and turn this into a pure integer program. And there's a benefit of doing that because you can then see that the strong inequalities aren't so much stronger than the weak ones. And so there's this notion, take Amitabh's class, I'll tell you all about this, of this rank of inequalities. And let me just tell you geometrically that if you look at the weak formulation and you think of the continuous relaxation, and you take a hyperplane defining an inequality that's valid for that relaxation of the weak formulation, and now you push that inequality in until it hits an integer point, anywhere, inside or outside the feasible region. If you do that in all possible ways, just refining the boundary a little bit, you get these strong inequalities. So the difference is really a small amount at the boundary, if you think about it this way. So what that suggests is strong and weak are really almost the same, and well, I want to try to get a better understanding of that. This is how I want to think about it. I want to go back to understanding why we saw this different behavior here. When the strong and the weak seem about the same, they seem about the same computationally in this nonlinear world where we had a quadratic objective, but in the linear world they seem almost the same. And you start to see why that can happen with this little cartoon here. So this is meant to be a feasible region of some relaxation, and we're looking at just pure integer points, and we have quadratics. That's the minimizer of the quadratic. And the minimizer of the quadratic may not be anywhere near the boundary. So refining the boundary is a useless thing if the optimal solution might be in the middle somewhere. And that optimal solution could be quite far from the optimal integer points, which are here. And these optimal integer points may be nowhere near the continuous optimizer, may be nowhere near the corner points, which would be optimal for a linear objective. So what are we going to do about this? We can't somehow, in the nonlinear world, think of improving the boundary as a good paradigm, which is how for years we've been thinking in the linear world, that we should just refine the boundary, and with a linear objective we'll always be at the boundary in the optimal solution, and that's the thing to do. In the nonlinear world that seems like it's not the thing to do. And so how are we going to compare relaxations? And the way I talked about here in this room 25 years ago was looking at the volumes of these polytopes to try to compare the relaxations. So this is just one way to cook it up. You can cook it up in different ways, but the basic idea is I have two relaxations of the same set, convex relaxations, and I'll compare the volumes. This way, it's normalized in a certain way. So the way to think about this measure is I take two concentric balls of the same volume, so the volumes of P and Q, these two relaxations, and I just look at the radial discrepancy, and I think of that as the difference between these two bodies. But you could look at the ratio of the volumes, whatever you want. It's just like if we can compute these volumes, you can cook them up any way you want to compare them and do asymptotics or whatever you like. And so that's one thing I talked about back then. Now, this seems like a really awful idea because computing volumes of polytopes is hard. It's sharply complete. And the thing is this, though, that it's hard computationally for arbitrary polytopes. But I'm trying to get some mathematical insights into very special models that have a lot of symmetry. And symmetry is the bane of computation, but it's what we hope for if we want to make some high dimensional statements mathematically, that if we can see this symmetry, maybe there's really less going on than we think. And so we're going to take advantage of symmetry to try to make some mathematical observations, not computational ones. So Brightwell and Winkler showed this problem as a really fundamental paper, that this is sharply complete. And the way they did it was they looked at special polytopes called order polytopes. And so the order polytope of a partially ordered set, you just, if I is less than j in the partial order, I have xi less than or equal to xj, and I think of this as the solution set of those inequalities in the unit d cubed. And well, if you think about this, so if I can get the volume, we'll see, if I get the volume of the order polytope, that is exactly the number of linear extensions of the partially ordered set divided by d factorial. So that's how they showed that this problem was hard. They showed the counting number of linear extensions of a partially ordered set is hard. So you can think about a total order of the variables this way. And a total order, there's, if you count it, it's d plus 1 inequalities in d split case, and they have, it's a simplex, and these are the extreme points, which is kind of strings like this that are full to the left. And these are the extreme points of that simplex of a total order. And then, well, the volume of the simplex is easy to calculate. It's just a determinant divided by d factorial. And then you can think of these d factorial simplices as every possible ordering. That forms a triangulation of the unit d cubed. And then for a partially ordered set, you can just see that every linear order contributes one of these simplices to the volume of this order polytope. And so if you add these up over all the linear orders that are compatible with the partial order, this is why it's equivalent to calculating the volume of this polytope. Now this all seems very bad because usually we can't count the number of linear extensions of a partially ordered set, but sometimes we can, and I can get some insight from it. So this is an example I talked about again last time, and maybe I'll skip it, but let me just say a few things very quickly. So we look at the fundamental constraints that are different between the strong formulation and the weak formulation for facility location. And there are very simple arguments that you can calculate the volumes of these polytopes. And what you can eventually see, and this is where I'll skip some stuff just to advance us along into this millennium, is that there are situations where that measure of the difference between the two polytopes goes to 0. So situations where the number of facilities is growing very slowly compared to the number of customers. And then these polytopes really are almost the same according to that measure that I gave you before, that radial discrepancy. And so what it means is that it's not surprising that the weak formulation is actually pretty good. It's not so much worse than the strong formulation when you have a small number of facilities relative to the number of customers, which is probably the actual state of affairs for real application. So the takeaway is that the idea that you should always use the strong formulation doesn't really apply in the case of nonlinear objective functions, and there's a mathematical reason why that can happen. That these polytopes volume-wise are really almost the same. So now I want to switch to some more recent work. It's called a Boolean quadratic polytope, and this is joint work with Daphne Skipper, who's sitting right here. So this is a really fundamental polytope in combinatorial optimization. It's very closely related to what's called the cut polytope of a graph. But in some ways, it's a nicer way of looking at the cut polytope. So what you have is a graph on vertex set V, and the Boolean quadratic polytope lives in this space, which is the number of vertices of the graph plus the number of possible edges of a graph on n vertices. So I'm always going to think about it in the space of a complete graph, but the graph might be sparser than a complete graph. And all it is, I take these x variables and y variables. So the y's are for pairs of vertices, and the x's are for single vertices. And I just impose these conditions on binary solutions. That if there's an edge of the graph, then if I set both endpoints to 0 or 1, then the y should be set to the product. So the only case where y is set equal to 1 is when both x's are 1. And so I get charged for that edge when I select both of the vertices. And in this way you can model all kinds of clustering problems, cut problems, lots of problems that are kind of combinatorially interesting, where you choose sets of vertices, but you kind of pay for edges. So there's a natural relaxation of this problem, and this is nonlinear. We don't like this, so we relax it to a convex set, and we relax it this way. And these inequalities kind of are very easy to understand. If either vertex is equal to 0, then the product should be 0. So these being 0 shuts down these variables. And if both of the endpoints are 1 for an edge, then that turns that variable on. And the y variable should be on. So the 0, 1 solutions to these inequalities are exactly the 0, 1 solutions here. But these inequalities are implied by these, and the opposite is not true, but this is a nice convex set. So this is a standard relaxation if you want to impose these kind of equations. And we want to try to get some understanding of when that's a good relaxation, how bad it is if it's not, etc. Padberg showed a long time ago that, in fact, if the graph is a forest, then this is the Boolean quadratic polytope, meaning that the convex hull of the 0, 1 solutions to this nonlinear equation is the same as the convex hull of the, is equal to the solution set of these inequalities. Okay, so the Boolean quadratic polytope is the convex hull of the 0, 1 solutions to this, and this is a description of that convex hull when the graph is a forest. So there's not much more to say when the graph is a forest. So we want to think beyond forests. Well, first of all, it's going to make our life easier just to realize that if the graph has several components, we can just calculate the volume for each component and multiply these all together. That's very easy to see. There's also the order polytope is hiding here. So this is an order polytope. If I make a partially ordered set where each vertex covers in the partial order the associated edge variable. So there's a nice order polytope except for these last inequalities. And it turns out the volume of this polytope is related to the volume of the order polytope. So the volume of this relaxation is always the volume of the associated order polytope, where I drop those last inequalities, divided by 2 to the number of edges. And so what you have to do is count the number of linear extensions of the partial order that's associated with that order polytope, and you get the volume. We were able to do this for complete graphs and get a closed formula. So complete graphs, remember I said before, symmetry is our friend. Complete graphs have a lot of symmetry. And so you can count the number of linear extensions of that partial order and get a closed formula for what the volume is of that relaxation. You can now take this and say, well, what if the graph is a matching? Then you put those last, that lemma together with this, and you can get a closed formula for the volume of the Boolean quadratic polytope for a matching. A good open question, if you want to try to work on this is the relaxation of the Boolean quadratic polytope complete graph. How far is this from the actual Boolean quadratic polytope complete graph? So that's getting an inequality description of the Boolean quadratic polytope complete graph. It's an impossible thing to do. It's NP hard to optimize over that polytope, so you don't expect a good description of the polyhedron. But still, it seems possible to get a good upper bound on that volume and show that it's really quite far from this relaxation. So that's something I've been thinking on and off about for a long time, but I don't have any progress on that. The other natural question is, what about non-complete graphs? Can we say anything? And that's what I...
So
yeah.
you want a lower bound on the...
I want an upper bound on the volume of the smaller polytope, the actual Boolean quadratic polytope. And I want to show that that volume is really much smaller than the volume of the relaxation. That's my guess. It's probably much, much smaller. So an upper bound, yeah. So you think, we're getting an upper bound, you're going to take some nice, well-behaved valid inequalities for Boolean quadratic polytope and show that that relaxation is a lot smaller than the actual Boolean quadratic polytope. But things get out of hand very quickly with losing symmetry when you start adding inequalities, and it gets hard to calculate things. So on the sparse side, though, you can say quite a bit. And so here's a few results we have. This is surprisingly complicated to prove this, but if you have a star graph, so a single vertex linked to everything else in a star, on m edges, then the volume of the relaxation, well, it's a farce, so the volume of the polytope and the relaxation are the same, and there's a formula. You think such a simple formula, there would be a simple proof. We only have a long proof of this. So that would be kind of cute to see a shorter proof of this. Things get crazier pretty quickly. So for a path, it's actually a complicated formula. So what are those A's? Those A's are well-known numbers in combinatorics. So there's a notion of an alternating permutation of the symbols 1 through k, where the symbols alternately become greater or less than the preceding entry. And the Euler number, AK, is the number of these alternating permutations. So they go like this for a while, and those are the numbers that come up as volumes of these polytopes, up to some constants. These are also the coefficients of the Maclaurin series for secant or tangent, the odd ones for tangent. And so that's a little indicator that these volumes of Boolean quadratic polytopes of paths are absolutely fundamental objects. They come up as coefficients of the Maclaurin series of tangent. That's kind of cute. Oh, you can say a little bit more. Cycle. So cycle is the first kind of the most interesting, simple, non-farce graph. And so here's a case where we can get the volume. It's very similar to the volume of a path. Still odd Euler numbers here. But we can also calculate the volume of the actual Boolean quadratic polytope for a cycle. And it's that volume minus something. So let me just give you a little hint of how that goes. The difference between the actual Boolean quadratic polytope on a cycle and the relaxation are these extra inequalities that you have to add in. They look a little obscure. They roughly have to do with the fact that a cycle and a cut in a graph cannot meet on an odd number of elements. But that's thinking about it in the cut language. In this Boolean quadratic language, it's a little more obscure, but that's really saying the same thing. So you take any cycle of the graph, you'll get an odd subset of an A, and you're able to write down this inequality. There's lots of odd subsets. So these polytopes are very different combinatorially. There's an exponential number of inequalities of this type that you have to add to that first relaxation I showed you to get the polytope. So they're completely different objects combinatorially, but the volumes are not too different. They only differ by this much, which we'll see later is not so much. Well, that's something about what these look like. You can understand, these are just examples for a triangle. So subsets of size of 2 or 3 from a cycle of length 3. And you can see that these are valid. If that variable and that variable are on, well, the only way they can both be on is the x1 variable is on. Because the only way that's on is if you pick 1 and 2 and you pick 1 and 3. But if you pick 1 and 2, you certainly pick 1. And then if you pick 1, 2, and 1, 3, then you pick 2, you pick 3, so you pick 2, 3. And you can analyze all these that way. They're a little strange, but they all have these combinatorial explanations. They're not actually, generally speaking, facets of the Boolean quadratic polytope of an arbitrary graph, but they are the facets. You need every one of them for the Boolean quadratic polytope of a cycle. So you really need all of these kind of complicated ones for cycles. So the way you show that theorem about how much you cut off, you show that every odd cycle inequality removes a disjoint part of the Boolean quadratic polytope. That's just a page maybe to show that. So I take two odd cycle inequalities for different odd subsets of a cycle. They cut off disjoint parts. And then you show that each of them cuts off exactly the same volume. And so if you go back to the formula, and that's really a huge amount of work that I have to admit was carried out by Daphne. I was just cheering her on while she figured all that out. So that's how many odd subsets there are of an m-edge cycle, and that's the 1 over that is the amount of volume cut off. And it's somehow a pretty messy proof to see that. So let me just skip ahead to this. If you look at the cycle now and do some asymptotics, as I said, they have very different numbers of inequalities. The relaxation has just 4 m facet defining inequalities, and the Boolean quadratic polytope of the cycle has that many more inequalities. So they have very different inequality descriptions, but the volumes are really very, very similar. These little pieces you're cutting off, there's a lot of them, but it doesn't add up to much. So if you do this kind of asymptotics where I look at the volume and I divide by 1 over the dimension of the space, this stabilizes to some constant a little bit less than a half. If I look at the difference of the volumes and do the same thing, don't worry about what that number is. I put an m here, and m is what's blowing up here. So if you think about bringing the m over there, this is decaying to 0 very quickly. So these polytopes volume-wise are almost the same, even though there's a lot of stuff going on the boundary which makes them combinatorially very different. There's a message here. It says important, so it must be. If you analyze the Boolean quadratic polytope in a cycle of length 3m versus m copies of triangles, so you think like maybe those sort of behave the same. They behave very, very differently. So for a long cycle, there's lots of facets, and if you include them, you're not cutting off much volume. But the same number of edges here, but a bunch of triangles, you better use those triangle inequalities. They cut off a lot of volume, and there aren't as many of them. So that's this nice, somebody in the polytope world is smiling down and saying, when there's lots of inequalities in this case, you don't have to include them, and when there's only a few, you should include them. That's a nice thing. It would be much worse if it was the opposite. So I think there's some other reasons why this is going on, but that's kind of an interesting message. That for Boolean quadratic polytopes, if you're really doing computation, what I would do is I would look for the short cycles in the graph and include all the inequalities that come from those, and that's probably enough. Let me mention a few other things. We can calculate in polynomial time the volume of that relaxation, this without the cycle and odd cycle inequalities, for any graph of bounded tree width. If you know what that is, it's basically a notion of structured sparsity in a graph, and it includes many nice classes of graphs.
What is a cactus?
A cactus is a graph where